Hello. This is chapter 2 of the book Mathematical Interest Theory. The title of the chapter is Equations of Values and Yield Rates. Say sometimes we wanted to say buy a house in 5 or 10 years, and we save money, say put money into an investment account monthly. And sometimes we don't have money, and we would withdraw some money from the account. So we will have a cash flow, and we wanted to calculate the accumulated value at the time when we want to buy a house. So this is one situation, and we wanted to find the future value. And another situation is that if we wanted to accumulate a certain amount of money, and we try to figure out when we are able to reach that goal. Yet another situation is that we have two uh, investments or two cash flows, and we wanted to compare which one is better by calculating the returns. So all these things will be discussed in this chapter. The materials in this chapter is kind of essential to the following materials. The first situation we wanted to deal with is relatively simpler when we have only one single deposit. Okay, and then usually we use compounded interest scheme. And this is the formula we use throughout for this in this section. Okay. AT is the amount or it's the future value of the account. A0 is the principal, and then you have 1 plus I to N. I is the annual effective rate, and N is the number of years. And when when we have a nominal interest rate compounded m times a year, we have this formula instead. Okay, so now we have a m times t compounding periods with the effective rate of interest per time period to be this quantity. Okay, so normally what we wanted to figure out one unknown quantity given the other known quantities. For example, sometimes we want to find out the principal. Sometimes we want to find the time. Sometimes we want to find the interest rate. Okay, so let's have a look at a couple of examples. All right, so this example. Knowing an annual effective rate of 8%, so this 8% is I equals 0.08. 5 years later, an investment grows to so much money. This is A out of 5 years. We're looking for the deposit, which is A of 0. So that's what we're looking for. We look at this formula, A5 equals A of 0 times 1 plus I. We do have the annual effective rate, and then to the fifth. So A of 0 equals A5, which is 3.32 over 1 multiplied by 1 plus 1.08 to the negative 5. Okay. And the solution, let me just show you the answer. I think that's about it. Um, All right. So let's move to the next problem. Adam deposits $500 in an account for his daughter that grows by compound interest. After 5 years, the balance has grown to $463.71. Assume there's a constant annual effective rate I earned by the account. Find I. So we're looking for the interest rate I. So we lay down the equation. Okay. The future value is that equals the deposit times 1 plus I to the fifth 5 years. So we have this number equals 1 plus I to the fifth. So I don't recommend you using a log function. Instead, it's better to use the root function. So I have this amount raised to power by 1/5. That's 1 plus I. And we can solve for I. Okay. Um, that is 0.03. Okay, so that's 3%. Next problem. Chen opens an account with $1,000. The account earns an interest, an annual effective rate of 4%. Chen learns that the balance is currently $1,342. How long did it take to earn uh, the $342 of interest? We're still using the compounding interest type of a scheme. So we have a 1342 equals 1000 times 1 plus I, which is 0.04 to the t. We'll actually look for t. Currently, so you really don't care when it is invested. You can assume you invested. So Chen invested the $1,000 at zero, and at time t, he's looking at the balance. Or you can consider, currently is like now, and once $1,000 was invested T years ago. So it's either way. It's just about how long, which is T here. So we solve for T. We have 1.342 equals 1.04 to the T. You're going to use log function to find the exponent. So take log. All right, and you can find T to be log of 1.342 over log of 1.04. Uh, if it has decimal, you just keep it. Okay, so 7.5 years. All right, move on. In reality, when people try to find the number of years to double the principal, they usually don't use the formula we like use it for using the formula we discussed earlier, and normally you need to take a log. So this rule is called the rule of 72. So you basically divide by 7, you divide 72 by the interest rate in terms of percent. So when the rate is around 8%, this rule works relatively well. For example, if you have 8% interest rate effective annually, and then it takes about 9 years to double the money. 72 divided by 8. When I is closer to zero, and then the rule would be slightly different. You have a 69. When I is getting bigger, then the number it should in terms of 72, it should be bigger. So when I is around 1.2, sorry, 0.12, so 12%. Uh, the numerator would be 73, and if I is close to 20%, then we have rule of 76. It's just that these estimates are better. Those approximations are better when you change 72 to 73 when I is around that and so forth. Uh, it has something to do with a linearizing log of 1 plus I. Sometimes uh, the approximation is better for different values of I when you have a different numerators there. Okay, so that's about this rule. Uh, so I think what you should be aware of is that the rule of 72 works well when the interest rate is around 8%. When the interest rate is far away from 8%, then the rule of 72 may not be good. Okay, so just remember that. Okay, so let's talk about the when we have a cash flow instead of having one single deposit or one single uh, borrowing. So we have this cash flow, C1, C2, and so forth, Cn, at time T1, T2, and Tn. And we assumed accumulation function is A of t. Okay. And the balance at time capital T, so normally capital T is somewhere here. So it's here. What you do is to discount everything back at time 0, and then you add them up, and then you uh, then put everything back, not back, I mean, you accumulate to time T. Okay, that's what you do. All right, so you look at the formula. You have CK divided by A of TK. So it will put the value of CK to the time 0. And then you multiply by A of T. Okay. At time tau, you basically multiply this actually V of TK. So divide by A of TK. You add them up, and then you multiply A of tau. So it's like you have the present value of everything add together and then move on to somewhere here. So it's tau. And at time 0, then obviously you just have uh, the move everything to discount everything back to time 0. So you have a C of k times, this is 1 over A of a T sub k, okay, the discount factor. Um, that is the B. B is the balance at time capital T, and it discount back to time 0 by multiplying V of capital T. Okay. All right. So let's have a look at a few examples. The answer is already here, so but that's okay. So an investor can invest in the project, which requires an investment of so much money at time zero, and investment pays so much time at time one, and so much time at two. The investor's capital is currently earning a compounded effective annual rate of interest, 4.5%. This is our I. Should investor invest in the project? So whether the investor should invest in the project depends on the net present value to be positive or negative. Okay, so considering the investment is negative number because it's out of the pocket from the investor, and then you have a positive cash flow for the following two time periods. So if we draw a timeline, okay, and this problem is relatively simple, so you both probably don't need to do that, but normally, usually I do that. Uh, so you have time zero, time one, time two, and the cash flow. So you have a investment, so negative 37400, and you have a positive 25000 and 15000. So we just find the net present values, and PV equals negative 37400. That's the value of the investment at time zero. But then you plus 25,000 times 1 plus 0.045 to the negative 1. And then you have 15,000 times 1.045 to the negative 2. You calculate it, it's positive, then you say yes, the investor should invest in the project. All right, next problem. A company has cost of capital of 7.5% as an annual effective rate of interest. Why it's called cost of capital? Because you have opportunity to invest your capital. So you invest in this, invest in that. Obviously, there's a cost. Uh, Sometimes the cost can be viewed as interest rate. Okay. Uh, if you have a higher cost of capital, then you have a higher return. Okay. You should have a high return. Okay, so we have two investment projects which have the forecasted cash flow. Both have an investment of $20,000. Project A gives $25,000 at time 3 and $10,000 at time 10 at time 4. And project B will give the investment return of $10,000 at time 3 and $26,000 at time 4. The profit made on each investment, you basically add what you get and subtract the investment. So the first one would be 15,000 and the second one would be 16,000. So the second project has higher profit, but the which one has a higher net present value? Uh, we actually need to compare the present value, the net present values of these two projects in order to determine which one is better, because The difference here is for project one, the large amount was paid at time three, while project two is paid at time four. Uh, the later the time, the later the bigger payment paid, the present value would be smaller. Okay, so imagine you have 1,000 years later, then this money really uh, doesn't worth much right now. So we sort of calculating the net present value for each. We do similar thing as what we did for project A. So net present value for project A, that is 20,000, negative 20,000 plus 25000 times 1 plus 0.075 to the negative 3 plus 10,000 times 1.075 to negative 4. And the net present value for project B is similar. We just change some numbers. And the answers are given here. All right. Okay. So project A has higher net present value. So uh, in the world of interest, we would consider project A better. All right. So next example. Joe wishes to borrow a sum of money. In return, he is prepared to pay as follows: $100 after 1 year, $200 after 2 years, $300 after 3 years, $400 after 4 years. Uh, if I equals 12%, how much can he borrow? This is basically to find the present value of this cash flow. The present value of the cash flow. So it will be 100 times 1.12 to the negative 1 plus $200 times 1.12 to negative 2. Okay. All right. The answer is here. Okay. Next problem. Helen borrows $5,000 from her credit card account at a nominal annual interest rate of 20% per year, convertible monthly. The interest rate is pretty high, but that's normal for credit card. 2 months later, she pays $1,000 back. 4 months after the payment, she borrows $2,000. How much does she owe 1 year after the loan is taken out? All right, so let's draw a timeline. Okay, so at time zero, Helen borrows $5,000. Okay, and 2 months later, so let's just use 2 months. 2 months. She pays, so it's negative 1,000. And 4 months after the payment, so that's another 4 months. So that's 6 months. You have she borrows again $2,000, and that 12 months, like 1 year, how much she would owe the bank. Okay. You can change average to 1 year, but probably it's a little bit better to use monthly effective rate because you have the interest rate is such a nominal rate monthly. So this is 0.2. The J, which is the monthly effective rate, is this. So the future value, let's call it future value. So 5,000 times 1 plus 0.2 over 12 to the 12th. Okay, so 12 months. So this is the monthly rate and this is the number of months. So they match. And then minus $1,000 times 1 plus 0.2 over 12 to the 10th, because actually you have a 10 months for this value to be accumulated. And then plus 2,000 times 1 plus 0.2 over 12 to the 6th. Okay. So you calculate it out, you would get a number, right? Actually, you can use Excel to do that. It's pretty not that bad. Okay. Let's see. Oh, I have a, well, I probably won't show you this side. Let me check. Right. So, uh, yeah. Okay, that's it. I was looking at the Excel sheet. All right. Okay. Um, so let's move on to a slightly different topic. Okay. So we still have this cash flow. And this capital C is lump sum of all the uh, investments, say, for example, or payments. And we wanted to figure out at what time T, capital T, such that this lump sum and whole cash flow have the same present value. Okay, so the whole cash flow will be equivalent to the lump sum capital C at time t. All right. So we're going to have this equation because they have the same present value. And I have C times use V sub V sup, I mean V to the T, which is the discount. Okay, V of V to the T is the discount factor. You can consider it as, for example, 1 plus I to the negative T. Okay, so V of capital T is 1 plus I to the negative T. This should be the same as the present value of the cash flow. So C sub K times V to the T sub K. Okay, for you sum up all these present values for for each uh, in payment. And you divide both sides by capital C, and you have V to the capital T equals the sum of C sub K times V to the T sub K, divide by C. And by the way, C is a constant with respect to K. And then you take log on both sides. You have a T times log V. So I move this log V to the right side. So you have a summation C sub k times v to the t sub k over c times log v. Okay, v is 1 plus I to the negative 1. Okay, so this is the exact solution of the time. Hold on a second. I think I forgot yeah. No. Actually, need to look at t. Yeah, I jumped one step and then some mistake happens. Let's do it again. We have t times log of v equals the whole thing in the log. So actually, what I wrote was quite different. I mean, I forgot to log on the right side anyway. Whole thing, and then divide by log of v. Now I can get rid of this log of v. Okay. All right. So let's see so sometimes a log is kind of annoying to calculate to use. So people actually use a different way, which is an approximation, which is called the method of equated time approximation. The time t with a bar is calculated by the weight sum of the time with weight ck over c. Ck is the case payment out of c. Okay, so that's kind of weight of ck in c, and then multiply the time, add them up. So to get this formula, it's basically you try to linearize v to the tk and log v. Okay, I'll show you quickly. If you're not interested, you can sort of skip this. So we have this of this exact solution. Okay. And v to the tk is 1 plus I to the negative t sub k. Okay, so we're going to approximate it by a linear function. You probably have learned it from calculus, Cal 1. So the numerator becomes log of the summation of ck over c times 1 minus t sub k times I. Okay. Let's not work with log yet. I want to simplify the summation. If you, what do I do? Okay, so you, the summation of this thing, is, oh, I needed to actually do a little bit further approximation. Let me think about it. Yes, okay. So you take a summation and it is, let's break it up. Ck over C, okay, minus Ck times T sub Ki over C. And this is actually 1. Okay, this is just 1. The summation of Ck equals C. So it's 1 minus this quantity. We take log, okay? There's a log here. And then we use another approximation, which is also from Cal 1, log of 1 plus some x, which is about x when x is small. So when you take log to the numerator, you would have negative the summation of ck over c times t sub k times I. That's the numerator. And then the denominator is very similar. Log v is what? Log of 1 plus I to the negative 1, which is negative log of 1 plus I. That is about negative I. Okay. So negative cancels out, and it's I cancels out, and you have this quantity which is in the next slide. All right. So you also need to know this name, method of equated time approximation. So when you see that, you need to use this formula. Okay, it's not the exact solution. We have this fact. It has something to do with again with approximation. Yeah. Okay. All right. So let's have a look at this example. The payments of $300, $100, and $200 are due at the end of year 135, respectively, assuming an annual effective rate of interest 5% per year. Find a point in time at which a payment of $600 would be equivalent. Okay, again, we are looking for capital T. All right, let's draw a timeline. So it's time 0, that's 1, that's 2, and 3. Payment of $300, $100, $200 here. Oh, sorry, 135. So let's get rid of the rewrite. So I needed 1, 1, 2, 3, 4. Okay. Not evenly distributed. 1, 2, 3, 4. I think I can make it a little bit longer. This is not important. Just a bit look a little bit better. Okay, so $300 at time 1 times 3 and 5. Okay. So we'll calculate the present value, or net present value is 300 times 1.05 to the negative 1 plus $100 times 1.05 to the negative 3, and then plus $200 times 1.05 to the negative 5. Let's see, do I have a number somewhere? No, I actually don't. Let's see, I don't. So I'm gonna just keep it like that, okay? And then this should be equal to $600 times 1 plus 1.05, okay, 0.05 to the negative t. Let's use time t or capital T, doesn't really matter. And then solve for t. All right, so you find the present value, you take log. So you have a log of PV over 600. That equals negative t times log of 1.05, and then you solve for t. Okay, so this is the exact time. Now for the method of equated time, we're gonna just find the weighted sum of the time. So the total payment is $600. So you have 1 times its weight plus 3 the second time, and the weight of the money for that particular payment, and then you have 5 times 200 over 600. So that is our T bar or capital T bar. It doesn't really matter. Okay. All right. So we have two answers here. All right. Let's see. What is the next one? Do we have another problem? Yes. Okay. We have now this problem is from the textbook. A loan is negotiated with the lender agreeing to accept so much money after 5 years and again after 10 years with the same amount, then $30,000 after 15 years in full repayment of the loan. The borrower wishes to renegotiate the loan so that these three payments are replaced by a single payment of that. Uh, yeah, that's actually 54,000. You add them up, you get that. It is agreed that the new payment should have the same present value as the old sequence of payments if the present values are calculated using compounded interest at annual effective interest rate 4.5%. This is our I. Now, these problems are not focusing on switching the nominal rate and nominal discount rate, and, nominal interest rate, and so forth. So just give you the annual rate. So it's simpler in some sense. Okay, so the idea is very similar. So I'm gonna just lay out how we solve the problem, and then I think it, it should be fine. Okay, 5 years, and then you have 10 years, and then you have 15 years. 1 2 0 0 0 1 2 0 0 0, and then 30,000. All right, so the present value equals 12,000 times 1.045 to the negative 5 plus, again, that number times 1.045 to negative 10, and then you have that times 1.045 to the negative 15. Do I have a number for that? Yeah, I do have that number. That's actually 3285.8.16. I use Excel to calculate it. Then this amount should be also equal to 54000 times 1 plus I, 1.045 to the negative capital T, because it really says time T. So let's use that. And then you solve for T. Capital T is what? Is some number. Let me just look at the answer here, okay? 11.2862. I checked it. It should be okay. That's right. All right. Now, how about the using the equated time approximation? So you find the weighted sum. Okay, weighted sum with weights the weight of the payment to the total. So it's 5 times, let's put T bar equals 5 times this over 54000 plus 10 times Okay, and then you have a third, it's 15 times 30,000 over 54,000. You would get that number. Okay, it's 35 over 3 or something like that. All right. Let's see. I think that is about it for for these sections, and there are following sections. I'm gonna use a different recording. Okay. All right. So that's for it. I'll see you later. Bye bye.